Yeah, this will be pretty much a technical talk, so I hope you're prepared for some crypto stuff. So I'm going to talk about a proposal that now has a BIP number since this morning, BIP 324. Well, I call it the version 2 message transfer protocol. It's not a consensus change, it's purely a peer-to-peer layer change. It's not all about encryption, but mainly about encryption, and it's only a building block. So it's not something that solves a direct user need. It rather solves kind of a fundamental thing that will lead to eventually things we can use as end users. So what is the goal of that proposal in general? So it's adding opportunistic encryption, which itself is not really making secure connections, but helping to build secure connections. And it has some nice properties that it may eliminate non-detectability of observers, of detecting observing, and it's also kind of eliminating non-detectable message manipulation. Although only including a possibility of authentication. And it's also a chance to optimize the peer-to-peer protocol, which is kind of set in stone since Satoshi made the first client. And it's, as said, extendable with various authentication schemes. That's also why the proposal is split between encryption and authentication, so we can have an amount of possible authentication schemes. Why version 2 and what is the thing with BIP 151? Well, it was proposed years ago. As most stuff in Bitcoin kind of development, it's slow. Sorry for that. BIP 151 kind of is dead now, and I could not alter it because people have started to implement BIP 151, so it would kind of be unfair to alter it, and then it's confusion about what version of 151, so it's like, it's dead now. And also there's some major differences that I was then figuring out version 2 makes more sense to call it then. There's also new service flag, new message structure, so it's not purely about encryption, but mainly. Yeah, why encryption? I mean, that question comes up first. I mean, the blockchain is public, right? I mean, blocks are public, transactions are public. Yeah, that's true, but the traffic, the peer-to-peer traffic is not meant to be, not meant to be public. Where transaction are originally coming from, that's data we don't want to kind of be public. And also we know that the Bitcoin network is under active surveillance. Chain analysis and other tools are kind of doing that. And encryption with the possibility of authentication may eliminate passive observing. And again, it's a building block. The potential that will be brought to the users lays above that layer. Also, it's not inventing crypto. Sometimes people said in the past, well, we shouldn't cook our own crypto. There's like tools for using that. There's TLS 1.3 now, which looks like stable. There is like Tor and whatever tool. Although, what we tend to do is like reduce the dependency set. So to have something that's stable and controllable with our own stack. Bitcoin Core made sure that OpenSSL is like outside of the consensus. Now it goes soon out of the code base. So we have a controlled stack of things we can actually make sure it's running. And there's nothing bad in running our encryption on top of Tor, which kind of, you know, not makes you trust fully on the layer where Tor lays. So it's only beneficial in that sense. So the things we use, it's again SecP 256K1 curve, the curve we use for general Bitcoin signing. We just use the Diffie-Hellman key exchange on that curve. Then a new construct is HKDF, which is super simple. It's basically hashing a hash or hashing a secret to get a key. It's also standardized in an RFC. Implementation is like 50 lines of code, super easy. Cha-Cha-20 is the main symmetric cipher, the thing how we encrypt data. I will talk about that later. And Poly1305 is a construct, also fairly old in quotes, and proven that will generate the MAC, message authentication code. So how's the handshake working? It's pretty simple. So when a node connects to another node, it not sends a version message first. It sends a 32 bytes pub key. So a pure pub key, no header, nothing else. And the responder reads the pub key and checks it. Does it start with the version 1 network magic, which is 4 predefined bytes, and has it the message version, which if those 32 bytes starts with that, it must be a version 1 connection. So it's backward compatible. So if that is not given, it tries to make the Diffie-Hellman key exchange by using private key, the own private key and the remote pub key, and also sends back its own pub key to the other side. So I assume now you're familiar with the Diffie-Hellman key exchange, so all these slides will also be then available later if you want to go over it again, no problem. So at the end, both sides have a shared secret without a man in the middle being able to kind of figure out what that secret is. And from that point on, they can enable encryption. And if it has started with the magic and the version string, it's obviously a version 1 handshake. I will not go into the detail with that. There are some slides. I will probably not have time to dive into those, but those are meant to kind of read later. This is a more precise form, what's happening inside the handshake. Well, some of you may have asked, pub keys are 32 bytes, compressed pub keys. Why 32 bytes? We're only going to take odd pub keys. If it's not an odd pub key during generation of a connection, you can just negate the private key and generate the pub key again, and you have an odd pub key. There's one slight beneficial thing of that. Because if you always send as a first thing 33 bytes a pub key, it's super easy to identify a Bitcoin handshake. I mean, it's not a goal of that protocol to make censorship resistant and to make everything random, because the traffic semantics are already revealing, the port are already revealing we're doing Bitcoin. But it's kind of a low-hanging fruit, makes it a bit more robust, a bit harder for super stupid package analyzing tools to figure out what's going on. And it's not really kind of reducing the security. It's not reducing the security. Once we have that Diffie-Hellman secret on both sides, we then use HKDF. If you're not familiar with the construct, you could imagine we're just hashing that secret in order to generate 4 keys and a session ID. The session ID has a nice property, which I'm going to show here. Because it's opportunistic encryption, which means we're not going to authenticate at that layer. A man in the middle could intercept that handshake, could stand between those connections. And he's just taking one side and kind of, intercepting the handshake as a traditional man in the middle during handshake, and just intercept keys on both sides. And initiator means he's talking to responder, but actually he's talking to the man in the middle, and the opposite. This is kind of without authentication, we cannot eliminate that, but there is the property of the session ID. So since we generate the session ID of the shared secret, that session ID can be compared. Not that this is practical, but it can be compared. It's similar to when you have a signal phone and you see that like very cryptic number you should verify with the other. You probably don't do it, but some do. And that already is usually pretty okay if some does that. because it may reveal if a man in the middle is there, only for a certain percentage of connections. And what's really important is, right now on the current Bitcoin network, if somebody is intercepting traffic, there is no possibility to detect that because we don't have any HMAC. So it's not possible to detect if anyone is manipulating packages or observing. With that proposal, it's theoretically possible. It's not included, there's no authentication scheme, but it's possible. So someone observing the network needs now to take the risk that he can be detected, which is very essential, in my opinion, for security. Peter Todd once said, well, it was like BIP 151 back then, provides an excellent defense against government attacks with man-in-the-middle capabilities. You can detect such attacks and change behavior. This is a huge improvement. Well, it's again taking the possibility of authentication in the case, but since it's possible to run a private, non-published authentication scheme on top of that, it's already a dangerous thing for somebody coverting package manipulation or observing. How does the rest of the internet solve that problem? There's two things we're usually familiar with. One is certificates. If we do an SSL connection, there is like a central list of companies that assure that kind of that static key is meant to be what it should be. But the problem is that's not something we want to have in Bitcoin, like a static list of centralized companies that verify others. And the other thing we're familiar with is the tofu concept. The tofu concept is once you connect to SSH, first time you usually get that fingerprint and you press yes. But what it means is if my first connection is man in the middle, I have lost, right? So it's like you trust on first use tofu. And this is also something we probably not want to have in Bitcoin. So that's why authentication is for now out of scope, and there are great possible proposals. People are ready to write them, and I think that's for later. So, but the goal was also, sometimes when you think about encryption, it's like, oh, I disable TLS because it's slow, right? Or I'm not using OpenVPN because my files transmit slower. Well, that was also a concern while developing that, but actually we figured out that version 2 protocol can be faster, and it even can be like less bandwidth or less bytes. So how is this possible? Let's first look at the message structure. So version 1, for those who are familiar with the peer-to-peer protocol, has that 4-byte network magic. That's always the static 4 bytes. And then there's the command, like inf, block. That's always 12 bytes. There are a length field of the payload, 4 bytes. Then, the crucial thing, we use a checksum in the current V1 protocol. And that checksum is a double hash, double shot to 56 hash over the payload and truncated down to 4 bytes. So it's a very expensive checksum. Satoshi made that decision, and we can get rid of that. So before version 2 or version 1, we have at least 24 bytes for each message. So version 2 means we can drop some things, optimize some elements, and at the end get down to 20 bytes minimum. How do we achieve that? Well, we first limit the size to 3 bytes. So that means a maximum message size of 8 megabytes. I will come to that, why it's 8 with 3 bytes. And we use IDs rather than string messages. So we can use a single byte for block, which reduces 5 bytes to 1. And there will be a larger checksum, which is then the MAC. That requires 16 bytes due to cryptographical requirements. So before an inf was always 12 bytes with a lot of zeros. Now it can be just 1 byte number identifying that this is an inf message. But still, we still want to allow string commands for extensibility for other message types. So whenever another implementation comes with another gigamec block is a good example, they can do it for sure. So this is a possible, the currently set table of kind of 1 byte to a message. What we need to avoid is central planning. So there's really no reason to overhaul the BIP every half year with a new command. So if somebody proposes a new message command, it should also propose the short ID. This is like a static set. Once made, it's static. This is the example of the new protocol, an inf. So you see an inf has currently a minimal size of 61 bytes. And it's even smaller with the new protocol. It's only 57 bytes. Yeah, why is the max amount of message 8 megabytes? It's because we're only using 23 bits. We reserve 1 bit for rekeying, for kind of using the next key in the symmetric scheme. So is 8 megabyte enough for a message type? Absolutely, because it doesn't mean we cannot send messages larger than 8 megabytes. It just means that's the maximum packet size. We can always like split up into multiple messages, which we should do anyways. So gigamec blocks still work. Rekeying, this is a cryptographical essential thing because usually, especially in the scheme we use, we cannot reuse nonces. So at some point, SSH recommends 1 gigabyte. We should use a next key, a next next symmetric key. So that's why a client can trigger in that bit that a rekeying should happen. Usually use hybrid schemes. That's in most of the crypto connection security, we use hybrid schemes, which means we have a Diffie-Hellman key exchange over an asymmetric cryptography tool. And after that, we use symmetric encryption, like AES, in our case, ChaCha20. ChaCha20 is an invention of Bernstein from 2008. It's fairly widely used. Android, so the current TLS connections use it. It's usually pretty fast if you don't have native instructions. If you have native instructions on your CPU, AES tend to be a bit faster, but where it matters, on low-cost hardware, ChaCha20 is almost always faster. And it's not vulnerable to kind of side-channel attacks, and it's actually a random stream, so you can pre-compute the random stream and then just use the XOR operations whenever you need an encrypted byte. We use a dedicated form of that scheme because we figured out a way how to optimize it for our traffic semantics. So originally, the ChaCha20 poly1305 construction was proposed by Adam Langley in an RFC, and OpenSSH kind of built that into their stack in a slightly modified form, optimized for their use case. And we have taken the OpenSSH version and also modified a little bit. Since I'm only having 20 minutes or 25 minutes, I'm not going into every detail, but how did we optimize it? That's still important. To kind of say what we have done is usually there's like the important one is like you do a ChaCha20 round for encrypting the length. So the OpenSSH version added that the length is encrypted. So it's theoretically possible to pad a message and nobody can figure out what was the length of that message. And they always call the ChaCha20 round, which always produces 64 bytes. So you compute 64 bytes, but then only encrypt 4 bytes with it. It's like throwing away 60 bytes of computation on every message. Maybe they didn't care, but in our case, we should care because, I'm skipping now a little bit, I analyze the traffic, and a third of our messages are below 64 bytes. Usually it's inf, ping, pong. These are the most transmitted packages or messages. So it's rather important that we optimize for that little message sizes. So that's why we changed the ADE construct a little bit, that we reuse the key stream of the 64 bytes and kind of not compute always 64 bytes. Details are described in the bib. Happy if you read it. Yeah, so it's basically telling us that we only use 2.048 charger 20 rounds in average, rather than using 3 charger 20 rounds. So it makes it a bit faster. What does that lead to? These again are the numbers of how many messages in bytes and in number a node things. It's not super representative. I don't have made like thousands of logs. It's just a single pair. But at the end, we can say, even for pruned ones, the amount of small messages are very large. These are the performance numbers of the current implemented scheme, which is a bit unfair because we're comparing highly optimized SHA-256 checksum against plain implemented SHA-20. So I think it's like comparing more to the side or helping more to the side of the SHA-20 in terms of it's faster. But still, we can see if we, on the upper left, if we have a 1 megabyte message, which is not the most used case, hashing 1 megabyte takes more time than encrypting 1 megabyte. So it's like almost twice as fast on an Intel computer. And the lower, the 3 charts on the lower end are on a RM machine, which is where it matters most, because there you will feel the hashing or the encryption. So you can even see that megabyte hashing a megabyte message takes slightly less time than encrypting. So in this regards, it will be slower with the current implementation. But if you look at the bottom right, you can see that small messages, encrypting is faster than hashing. And again, hashing is necessary for the current V1 protocol because we have that 4-byte checksum. So what I wanted to say, we can encrypt the traffic, we can make a building block, and it's faster, and it's less bytes. So I think there's a big opportunity to kind of make the peer-to-peer network more robust. It's not solving, I want to connect to my home node in the first place, but it's kind of a step towards I can connect to my home node, I can add node with not just an IP, I can really make a secure connection if I want to, and yes. So next steps. So we already have merged SHA-20 and Poly 1305 in the source code. Now the proposal needs more review. So if you know, or if you are a cryptographer or anyone who's really interested in that, please review. Take a look at the proposal, figure out what's wrong, figure out how to make it better. The whole thing is already open as a PR, so you can test and run it if you want, the whole encryption. And I think the goal should be that we can deploy it as experimental feature, so we don't, because it's a risky area, the peer-to-peer code is rather risky in terms if we screw up there, somebody can shut down the whole Bitcoin network, so we need to be careful about that. That's why it should be an optional feature at the beginning, even flagged as experimental, so people start to use it, and the longer we use it, the more stable it can kind of be as a default option at some point. Yes, that's it. Questions?
Hi. Is there a danger of segmenting the network if some nodes decide that they're only going to accept encrypted connections and other ones don't care.
Yeah, I mean, if we would not set like in stone at this state, everyone needs to use encryption, there is the risk of segmenting, but since it's like Tor is already there, it's like on a similar level than using IP version 6, Tor, IP version 4.
I understand that some people are concerned about like segmentation if some people require this, but on the other hand, the existing peer-to-peer protocol is entirely vulnerable to man-in-the-middle and can be segmented at like the continent level if governments decided to. So if you have a variety of transports with like tofu or like person-to-person authentication, then that's one way to guard against Sybil as well.
It may even help for segmenting, yeah. No questions. Good. Well.